All right, so we've been talking about thermodynamics and talking about delta H, delta E, and a little bit about our work energy, right? So here we have a chemical reaction, and we want to think about the delta H, right? That's the energy that's what?
Released in the form of heat.
That's right. How does delta E relate to our delta H?
E and H might be similar. H is the energy of heat, and then you have your work energy. So delta H plus the work energy equals our total energy, delta E.
Okay, very good. Good job. So, what do you think? Do you think this chemical reaction here has a delta H similar to that of delta E? Why or why not?
How did we know whether or not? So you're wondering if there's any work energy done here, right?
That's right. We want to know how much work energy is done here.
Oh yeah, I guess there's a lot of work energy done.
How do you know?
Because we start off with no moles of gas, and we get 4 moles of gas.
All right, very good. So let's calculate the delta H, and we'll see what a lot of work energy actually means, okay? So, can you calculate our delta H for us?
I guess so. So we got negative 241.8 times 6, negative 393.5 times 12, and then nothing for the nitrogen, and then subtract 3,862.9 times 2. Is that right?
That's right. So put that in your calculator. Make sure you get 13,898.7. All right. Now let's calculate for this reaction our delta, not our delta H, but our delta E, or the work component. We'll do the work component first, and then we'll look and see what the sum of those would be. So how would we do the work component?
That was, let's see, it's change in moles of product to gas to reactants, right?
That's right. So how many moles of gas do we have in the product side?
Let's see, 12, 18?
That's right. Well, no, 19, 20, 21, right?
Oh yeah, 21.
So 12, 6, and 3 here, 21. How many moles of gas do we have on the left side?
8.
Very good. So 21 minus 8 would be our change in moles of gas, right? Is that 13?
I think so.
So if we had 13, what do we do with that moles of gas?
Multiply it by 0.821.
Okay, so let's go back here. It's not 0.821, is it?
Oh no, it's 8.314.
All right, so it's not liter atmospheres per mole Kelvin, it's joules per mole Kelvin. And again, change in moles of gas, the R value, which, you know, R now just means gas constants used. So we will have different kinds of gas constants depending on what our units are. So we would, you know, be provided a table or look it up online, but we could tell that this was the right one because of the units that we want to have, our energy units. And we want to get rid of our moles and our Kelvin. So what did we say? 21 minus 8, 13, plus, or times 8.314 joules per mole Kelvin, right?
Yeah, okay, so times, what was the temperature on that question?
All right. Temperature on the question is 25 degrees Celsius.
So times 25?
Well, let's go back. Is that right?
Yeah. Oh no, it's in Kelvin, that's right.
That's right, so 298. So we get this 32.2 from, we'll do it on the calculator here. 21 minus 8, that's our moles of gas, times 8.314, times 298, that's our temperature in Kelvin. All right, so there's our 32,200 joules of energy. We convert that to kilojoules of energy, 32,000 or 32.2 kilojoules of energy. So even for a reaction like this, where there's a significant moles of gas, there are still 8 moles of gas to start with here, but there's significant moles of gas produced, we see that the relative energy released in the form of, what is this, heat or work?
Oh, that's work.
And this one over here,
That's our heat.
the relative amount of energy released in the form of work is what? Similar? Smaller?
It's about the same, right?
No, you see this is 13,000 and this is only 32.
Oh, but that's at 32,000.
But that was joules, right?
Oh, yeah, okay.
So then the sum of those two is our delta E. All right? Okay, good. So what's the internal energy for this chemical reaction?
Isn't that what we were asked before?
No, before we just did the delta H. Do you remember what the delta H was?
Oh, I don't. Was it 93.1? I think it was 93.1.
Let's go back to this question and see. Oh, it was negative 97.3. All right. So for this one, it's negative 97.3 for the delta H, right? And the moles of material here?
Let's see. Well, here you got 1 mole of gas in the products and 2 moles in the reactants. Can you still do it that way?
You can. You can. And actually, what that means is the reaction actually gains work, has work done on it by the atmosphere. And so your change in moles of gas are 1, that's moles in the product, minus 2, that's moles in your reactants. So it's a negative 1 times 8.314, and that's joules per mole Kelvin, 500 Kelvin. All right, so 8.314 times 500, whoops, that will be our 4,157, negative 4,157. No. Sorry. We didn't emphasize this enough back here. We have to go back to this before. That negative sign, the definition of the work is negative change in moles per RT, or times RT. So when we look at, we throw that negative sign in there because we want it to be consistent with our heat. So this is not a negative sign. It's negative N, delta N RT. And we throw that negative sign in there because we want the signage to be consistent between the heat and the work. All right? So our answer is going to be not the negative 97.3, but it's going to be the negative 97.3. Let me write it here, 97.3, whoops. Clear, negative 97.3 plus 4.157. All right? So our answer is going to be a negative 93.1. That is our energy, our internal energy, our delta H?
No, delta E.
That's right, delta E, because that's the heat energy and the work energy. Okay, good. Now, we have a definition called standard state, which is essentially the standard condition at which we speak of chemical. When we speak about chemicals, we talk about them in their standard state. So, for example, if I want to talk about oxygen gas, its standard state, this is just our definition, is 1 atmosphere of the material at the stated temperature, whatever it is. And if it's not specified, then we assume it's room temperature, 298, 25 degrees Celsius, 298 Kelvin. If we're dealing with a solution, then we say our standard concentration is 1 molar. And we have this little, we call it a knot, or a degree sign, but it's called a knot. So delta H knot. And that little sign there helps us know that we're talking about delta H at standard state conditions. All right? And so what we're learning here is that the thermodynamics of a reaction are dependent on these different parameters. The concentration of the material, whether it be a gas and therefore its pressure, or whether it be its a solution concentration of a chemical in solution, or the temperature. Okay, these things change the delta H, delta E for given chemical reactions. All right, good.